presentation today, we will begin with a brief overview of our MSPM0 portfolio, a quick refresher of all of the available devices as well as their key features. Then we will go deeper into our software development kit and available subsystem examples. After that, I will walk through a demonstration of opening and running one of our subsystem examples, showing you from start to finish how easy it is to develop using our subsystems. Lastly, we will highlight key resources available on ti.com to help you get started today. Overall, our MSPM0 microcontroller portfolio is designed to help reduce your system cost. First, our devices are manufactured utilizing a 65 nanometer wafer manufacturing process, which provides the best cost structure for microcontrollers, including our mix of digital, analog, and memory components. This allows for us to provide our devices at an optimal price for customers. Second, we are able to leverage the high-volume analog business here at TI to optimize our package offerings, developing smaller packages to keep your board space small and lower the cost of resources. Lastly, we also integrate Texas Instruments' well-known analog IPs into our design so that you can save on your bill of material cost. As general-purpose microcontrollers, the MSPM0 devices can fit into a broad range of applications, including factory automation, appliances, building automation, automotive, and more. The MSPM0 microcontroller portfolio spans across a wide range of performance and cost options. We offer three main families, including MSPM0C, MSPM0L, and MSPM0G. Starting on the bottom left, we have our MSPM0C devices. These are our lowest cost and smallest size microcontrollers that we provide here at TI, perfect for replacing 8 to 16-bit microcontrollers and general housekeeping functions as well. Moving up to the mid-range, we have our MSPM0L devices. While all of our devices are low power, our L series is optimized for power-constrained applications, with 71 microamps per megahertz in run mode and 1 microamp with retention and standby. With the release of our L122 and 222 devices in the darker blue, this family now spans from 16 to 256 kilobytes of flash memory. Lastly, at the top right, we have our MSPM0G devices. These are our higher performance and compute devices with 80 megahertz CPU frequency, math hardware accelerators, and dual 12-bit ADCs for simultaneous sampling. Also, all of the MSPM0 devices are pin-to-pin hardware and software compatible within the same packages. So if you start designing with one device and you decide you need more or less performance or memory, you can move up and down between families with ease. Along with our hardware, we also provide a free software development kit, better known as our SDK. The MSPM0 SDK is your one-stop shop for all of your software development needs. The SDK includes libraries, middleware, and stacks for specific applications, RTOS options, high-level and low-level drivers, bootloaders and secure boot, as well as multiple code examples to help you get started. These offerings help to increase the level of abstraction and provide a solid foundation for you to build your application code off of. So no matter your level of software experience, the SDK can help you design and get to market faster. Within the code examples, we have a section dedicated specifically to our subsystem offerings. Now, what exactly are subsystems? Subsystems are smaller functions that a microcontroller commonly performs. Here at TI, we provide several building blocks to help you address these common design challenges. For each subsystem, we provide step-by-step instructions, design insights, software examples, and suggestions for feature enhancements. While the subsystem code examples are plug and play and fully functional, you can also take the base examples and adapt them and combine them to meet your specific end equipment needs. Overall, the main goal of these subsystem examples is to provide a base to build off of to help you save on software resources. As a result, decreasing the time it takes to get to market. Our subsystems can be grouped into three main categories: general functionality, communication bridges, and analog functions. Here we have included a table showing a short list of some of the subsystems available today and the MSPM0 devices that they are compatible with. As you can see, some of the more analog or computation-heavy subsystems are only available on the higher performance devices, such as MSPM0G. Some examples include the PGA or digital filters. This is due to the processing power and analog integration required for that specific subsystem. Our team is continuously adding more subsystem examples in our software development kit and online. So if there's a specific common microcontroller application that you are interested in that isn't here, please let us know and we can work to add it in the future as well. Next, let's dive deeper into one example subsystem from each of these three categories. The first subsystem that we've chosen is an LED driver with pulse width modulation. As mentioned in the slide, this example utilizes multiple timers with PWM features to drive a set of LEDs. The goal with this subsystem is to show a simple but more developed example of how the devices can control a number of LEDs, and it offers a simple explanation on how to control the dimming rate. As you can see in the slide, we are able to control up to 8 LEDs using 4 general purpose timers. This is accomplished using the PWM and complementary PWM outputs. The MSPM0L and the MSPM0C families of devices are able to drive up to 4 milliamps of current from their I/O pins. The M0G family contains high drive I/O pins, which can drive up to 20 milliamps of current. All MSPM0 devices have open drain I/O pins, which are 5-volt tolerant and capable of syncing up to 20 milliamps. This subsystem would be useful for simple LED control applications, which can be found in a large number of end products. We have the corresponding software examples available in our software development kit today just to help you get started. The next subsystem we will investigate further is the UART to I2C bridge. This subsystem functions to interface a UART device to an I2C target device. It enables the UART to both write to and read from the I2C target device. It does so by utilizing a packet-based structure, where the UART device will first send a command to indicate read or write, and then send another command indicating the number of bytes in the transmission. Then, in the case of a write, the MSPM0 passes on each byte written by the UART device to the I2C target. In the case of a read, the MSPM0 begins to read from the I2C target, passing on the data it gets back to the UART device. This subsystem is available on all MSPM0 devices, as all of them contain both UART and I2C functionality. So it can be implemented with the smallest MSPM0Cs all the way up to the most powerful MSPM0Gs. If you are interested in developing another UART packet-based communication project similar to this, you can always take this example and use it as a reference. The goal with the subsystems is that they are modular and easily adaptable, so they can function with no adjustments, or they can shape to fit similar applications as well. This slide actually presents 3 subsystems that we've decided to lump in together for today's presentation. All of them consist of performing a single ADC sample on an external pin using the MSP's internal ADC. Then the device transmits the result out using the chosen communication interface, which can be SPI, I2C, or UART, with our current selection of subsystems. All 3 of these examples can be modified in a few short minutes to either continuously sample the ADC or to add some quick data processing in the code as well. Across our MSPM0 portfolio, we have different levels of ADC performance. Starting with our smallest device, MSPM0C contains one 12-bit ADC with a sampling rate of 1.5 megasamples per second. Next, our MSPM0L family has one 12-bit ADC sampling at 1.7 megasamples per second. This is a slightly higher sampling rate than our M0C family. Then at the top with our MSPM0G family, these devices have two 12-bit ADCs with sampling rates of up to 4 megasamples per second. All devices also have all 3 communication interfaces to pass on the data collected using these ADCs. The last subsystem we will go through today is the dynamic programmable gain amplifier. The goal here is that we can dynamically change the gain, output the amplified signal, and read the result with the ADC. Then, using the ADC measurements with the window comparator functionality, we can decrease the gain when the amplitude is high or increase the gain when the amplitude is low. This allows the user to maximize resolution with small input voltages with high gain, and also sample larger signals by switching to a lower gain. For this final subsystem, I'm going to go ahead and give a live demo to show the process of importing the project, flashing the device, and viewing the output using a logic analyzer. So now I will pause the presentation and move over to the screencast to show the process. In order to start using our subsystems, there are 3 things that you need to have at your disposal. First, the CodeComposer Studio, or your IDE of choice, downloaded. Here I have CodeComposer Studio, and you also need the latest version of our MSPM0 SDK software development kit downloaded. This can also be found on ti.com, and we have included the link as well for everyone who registered today. The last thing you'll need is the MSPM0 evaluation board or launchpad, and today I will be using the MSPM0L 1306 launchpad. So here, as you can see, I already have CCS pulled up, and I'll show you how to import the example and find it in our SDK. So here you can hit Import Project and browse. If you have the SDK downloaded, you can find it in your windows.c file and under TI. So if you click into here, you can see all of the TI folders, and I have multiple versions of the SDK, but we'll choose the latest version here, and then go into examples and no RTOS. And then, like I mentioned earlier, we're going to be utilizing the M0L1306 launchpad. So click into that. So just whatever launchpad you are using for your specific subsystem, you click on that one. And then we actually have a folder specifically called MSP subsystems here. So you can click into that and see a list of all of the subsystems that we have available. And we're continuously adding to this list as well. So today we're going to be doing the programmable gain amplifier one. So you can click onto that, select folder, and let's do the GCC and finish. So now that we have this downloaded here and imported, it has all of the available inclusions as well. We have the README file, which tells you exactly what pins are being utilized, and then the sysconfig file, which helps to show the configuration and everything that is being utilized in this design, including the ADC, the op amps, and the current setting there. And then you can also open the C file, so you can see exactly what we are doing today. So here is where the high margin and the low margin for the window comparator are set. The code then sets the ADC window comparator thresholds using those values. So if you want to change anything, you can change those up there. And then the interrupt handler here for the 12-bit ADC can help to read that there. And let me go back to the README just to show a little bit more here. Like we mentioned, the op amp is configured in non-inverting PGA configuration. The ADC is configured to sample the op amp output. The window comparator mode for the ADC is engaged to detect high and low ADC value boundaries. When hitting these boundaries, the op amp gain is adjusted to keep input signal in optimum bands of resolution, and the inputs are configured for easy connection to external circuitry. Here we have the op amp input on PA18 and then the op amp output on PA16. So we can I'll show you the configuration right now, and let me switch from the screencast to the camera real quick. And here we have the setup for the programmable gain amplifier subsystem. Here we have a desktop logic analyzer along with our MSPM0 L1306 launchpad. As you can see here, the yellow wire is connected to the waveform 1 from the logic analyzer, helping to provide the input onto pin PA18. And then we also have the blue wire also connected to that same waveform to help measure it on the scope as well, so we can get a visual view. Then we also have the orange wire here, which is connected to PA16, which is reading the output of the op amp in the programmable gain amplifier demo. And yeah, once again, here is the M0L1306 launchpad and the setup that we have. Great. Now that we have everything plugged in the correct configuration, we can go ahead and start the debug session to show you the code in action. So here you can press the debug button in the top left corner, and CCS will then continue to build the example code and start the debug session. Now that the buttons here on the menu are no longer grayed, that means that we are ready to continue, and you can hit the resume button and it will flash the device. Next, we can go into our associated application for our desktop logic analyzer. Here we have a waveform, just a simple triangle waveform with a frequency of 1 Hertz in a period of 1 second and an offset of 1 volt. So it will be going from 0 volts all the way up to 2 volts and back down again. And this will be our input for the PGA demo. Then we can go into the scopes that we have set up. The blue scope is representative of the input that we just showed earlier, going from 0 to 2 volts. And then the orange scope here is representing the op-amp output, which is also plugged into a PA16 on the board. So I can go ahead and get this running. So get the waveform running, and then in the scope, hit start. Great, now let's pause and we can start to explain the results here. So as we are increasing the input voltage, the op-amp output is also going to increase until we hit the window comparator maximum, and then you will decrease the gain in order to drop back within the range you allow. And then this process will happen again, and it will continue to increase until it hits that window comparator maximum, and you decrease the gain to decrease the op-amp output. And then once you hit the minimum programmable gain, which is 2 for the system, it will continue to increase until you rail out at 3.3 volts and stay consistent there. Then on the way back down, as the input signal decreases, you will continue to decrease your op-amp output until you hit the window comparator minimum. Then you will increase the gain, which will then increase the op-amp output. Follow the same process until you then hit the maximum programmable gain, which is 32 for the MSP op-amps, and continue to decrease until you hit 0 volts. Then the process repeats again and again. Great. Let's go back to CCS one last time and stop the debug session. As I mentioned earlier, our subsystems are designed to function as is, or you can also customize them to fit your specific application needs. For example, within the application code, as I mentioned earlier, you can change the window comparator values here, and you can also add in some and adjust some math factors in the main code as well for the interrupt handler. And then if you also take a quick look at sysconfig, we'll just do a quick high-level overview here since it's not a sysconfig presentation. But you can also edit all of the configurations here. So if you click into the ADC, you can adjust the sample clock configuration here. You can also edit the reference voltage if you wanted to use VREF instead of VDDA, and you can also update the pin muxing. So if you want to use a different pin for the 12-bit ADC, you can do that as well too. Then if you also click into the op-amp, you can follow a similar process to edit any of this, switch to inverting or non-inverting, and also edit the pin muxing as well to fit your specific application needs. That completes our demonstration of our programmable gain amplifier subsystem. Let me transfer back to the slide deck to share some final resources with you all. Now that we have gone through an overview of our subsystem offerings as well as an example demo, I wanted to share with you how you can get started today. First, we have a dedicated tool page on ti.com to highlight our MSPM0 subsystems. This page includes the documentation with the step-by-step instructions and insights, as well as links to the software examples. Also, the subsystems are organized on the page in the main categories we mentioned earlier. I have also included a link to access and download our MSPM0 software development kit. where you can find all of the subsystem code examples like we walked through earlier. Lastly, we have hardware launchpads for each of the 3 main families to help with your initial prototyping and testing. I hope this presentation helped to demonstrate the ease of utilizing our subsystem examples for your design. Thank you again for attending this presentation, and now we will use the remaining time to open up the floor for questions.
Thanks, Alex, for that great presentation. We already have several interesting questions, but I want to let our audience know that there's still time to submit your questions. So with that in mind, Alex, are you ready to answer some questions? Alex, can you hear me? I'm not sure she can hear me. Can you hear me?
Of course.
Oh, okay, great. Sorry. Probably a problem on my end. So, okay, well, guess what's right started then. The first question, are there any of the...
yes, I can hear you. Can you hear me?
Yeah, I can hear you fine now. Yeah. Okay, you ready to answer some questions?
Hello?
Can you not hear me?
I think it's lagging. I'm so sorry.
All right, I'm going to read the question, and then if it's lagging, maybe we'll have to deal with it. The first question is, are there any of the MSPM0 devices available, any of the popular sort of hobbyist prototyping things? I think they're talking about like Raspberry Pi Pico, STM32 Nucleo Nano, Arduino Uno Nano, that type of platform. Apologize for the lag. I think we're having some technical difficulties here. I apologize. I believe Alex is going to try to log back in, and so just bear with us. I'm sorry. Guess we have gremlins in the system today, which happens.
Oh, no. Hello, hello?
Yeah, I can hear you. Can you hear me?
Yeah. Is there a lag now?
No, there seems to be no lag. So I can repeat that first question again.
I think I got it. Thank you. Sorry for the technical difficulties here. I understand that the question is, are there any MSPM0 devices available in any of the popular inexpensive hobbyists and prototyping forums? On our side, like I mentioned towards the end of the presentation, we do have our launch pads available through ti.com for each of the main device families that we walked through at the beginning. We have one for M0C, 2 for M0L, depending on what level of functionality you need, as well as one for M0G. And these are just the superset variants of each of the devices, so you can help to get all of that functionality and prototype with that in the beginning too.
Got it. Next question. I guess we live in this day and age where the ARM M0 cores in lots of different companies' MCUs. What would you say in terms of what makes the TI MSPM0 better than, let's say, other ones from ST and NSP and that type of thing?
Mm-hmm. Yeah, so like I mentioned in the beginning of the presentation, a lot of our advantages come from our supply as well as our cost advantages that we have here at TI. We're able to leverage a lot of TI's well-known analog IPs and integrate those into our designs. And you have the backing of Texas Instruments as the main supplier, and we're moving a lot of our manufacturing process internal to help ensure some of your supply moving forward. And another great resource is just the support that we have through the company. We have various forums, including EDE, as well as if you have a dedicated TI representative, we can get help through that forum as well. So there's technical support as well from the business unit as well. And yeah, I think there's a lot of similarities, but we have that added extra oomph there with the supply and support from our side.
Yeah, those background issues are really important. Like, for example, like during the pandemic, the supply chain issue was a huge deal. And even coming out of that, people are really looking at it. So it's an important point. Yeah. Next question. What's the maximum clock speed that can be handled with the I2C MSPM0 MCU?
Yeah, I think we should also have Dennis on the call if he's able to hop in, but if not, I can help to link us to the data sheet there. It's I2C Fast Mode Plus, so it's 1 megabit per second for the sampling rate there, and I can help to double check that. I don't know if Dennis is on the webinar.
But that sort of information is in the data sheet, you're saying, yeah.
Yes.
Yeah.
Okay. So for each of the device families, it is we have a respective data sheet that's on ti.com. If you look in the handouts, we have the landing page for the ARM Cortex M0 Plus MCUs. And each of the device families we talked through have a corresponding data sheet, technical reference manual, samples, everything's all on there for you to find.
Yeah, okay, great. Next question, is there any tool for the TI-VA C series microcontroller? And there's a part number, I'm gonna read it too. It's TM4C123BE6PM, I love these very specific questions, to program it via serial UART instead of JTAG. That's a very specific question.
Yeah, yeah, I can definitely hope to reach out afterwards as well. But we do have ways to program our devices through UART as well, instead of through the JTAG process. And we should have code examples and explanation for that, as well as a resource I can help to share afterwards as well.
Excellent. Next question, is there support for using the MSPM0 SDK on other popular IDs such as VS Code?
Yes, we definitely have support. Our tools and software is compatible with multiple other IDEs, including IAR and Kyle. So if that's an ecosystem that you are more comfortable with, we can definitely help to support that. And the list of our supported third-party IDEs is also included on our online landing page on ti.com.
Okay. Talking about the subsystems that you mentioned, is that list a complete list, or will there be other ones added in the future?
Yeah, so this list is only the beginning. We are continuously adding more subsystems as customer needs arise. We actually just recently uploaded another 16 in the last week or so.
Okay, wow.
So yeah, so you should be able to see a couple more online now. And so if you have any specific subsystem needs that you're interested in that isn't on the current list, please feel free to let us know and we can add it to our creative backlog as well.
Excellent. Another question about subsystems. Could you explain the process of combining multiple subsystems? What would that look like?
Yeah, so as I was showing in the demonstration there, you have both the sysconfig file as well as the main C files as well too. And you can help to combine some of the configurations in sysconfig, so some of those settings. And you can also then take and copy paste from both the main codes, main C codes, and help to edit functionality there. So you can help to pick and choose what you want to reuse in between the two and use it as a base for moving forward.
Excellent. Next question. How does the MSPM0 MCU subsystem support scalability and integration with other components in a larger embedded systems?
Yeah, yes. We definitely help to support scalability both within our own portfolio as well as across the entire TI platform and other embedded systems. For our devices, we have hardware and software compatibility between each of our devices. If you're starting in the same package and you want to move around depending on your requirements for analog integration or CPU frequency, if any of those requirements change, you can move up and down without having to do any hardware or software changes, which is part of the reason that makes these subsystems so helpful and versatile, that you won't have to make any of those changes moving between. So that's something that can definitely help with the scalability of our portfolio. And in the entire embedded system, I think having that flexibility is definitely something that is beneficial. And like I mentioned earlier, we integrate some of TI's well-known analog IPs, so that can help with integrating some of the discrete analog components in your design and decreasing cost as well.
Excellent. Are these subsystems available for IAR? I believe they're referring to the embedded tools company AIR in this case.
Yeah, yes. I know we mentioned this a little bit earlier too, with the tools and software compatibility with different IDEs. So that includes IAR and Kyle, and we do have, like I mentioned earlier, all of those third parties listed on our website as well too.
Excellent. Next question, how do you know which subsystems are supported by which devices?
Yeah, of course. So it's pretty simple to tell which devices are support each subsystem. When you click into the application brief that's attached to each of the subsystems, you can open that respective design document, and there should be a section that highlights the compatible devices as well. So you can see which devices, whether it's C, L, or G, work with this specific subsystem. And another way to check is to also just look at the list of the required peripherals. Those are also included in that design document, and compare those with the peripherals that are available on the device that you're interested in. So as long as the device has all of the required peripherals, you can use them in the subsystem code example.
Great. Another question, what are the key considerations when choosing an MSPM0 MCU for IoT or low power applications?
Yeah, so all of our devices are low power and they have been optimized for low power applications. But the main one, if you're specifically interested in low power applications, would definitely be our M0L family. Those are specifically optimized for low power applications and have a power consumption of 71 microamps per megahertz in run mode and 1 microamp with retention and standby. So if you're in any sort of power constrained application with a battery or anything in that case where low power consumption is extremely helpful, I definitely think leaning towards our M0L family of devices is going to be very beneficial for you. But as I mentioned, all of our devices are low power, and you can always help to use some of our different low power modes, going from all the way down to stop, sleep, standby, run, everything to help decrease the power of your application.
Gotcha. Well, it looks like we covered all audience questions. I want to thank you again, Alex, for an excellent presentation. And I love an engaged audience, and I appreciate all the questions. So before we wrap up, I'd like to announce our prize winners for this session. Congratulations to Stephen Weeks and Gordon Margelou. I'm going to spell that last second name there, Margulix. So we'll be in touch with you within the next week to ensure that you have all the information you need to get your giveaway package. Thank you for attending Industry Tech Days 2024. And I want to thank our giveaway sponsor, DigiKey, and thank you to our event partner, Electronica. And if you happen to be in Germany, as I will be, November 12th through 15th, go and check out the in-person Electronica trade show in Munich. In a moment, you'll be redirected to Texas Instruments exhibitor booth, and I encourage you all to check out today's other live sessions, keynotes, and published content. Thank you again.